In this section, we're going to review the ways that we find distances to things out in space. And let's start with an overview. We call it the distance ladder. And it's the idea that if something is close by, we might use a different technique to measure its distance, like radar. But radar is not going to work for something across the universe. We don't have time to wait for the light to get there and get back to us. So for objects that are further away, we're going to have to use a different technique. One reason why it's good to call this a ladder is the idea that you can't get up the ladder without relying on the steps beneath you. So we wouldn't know distances to objects in the Milky Way if we didn't already know distances to nearby stars, and we can't even know that unless we know what the scale of the solar system is. This is condensed. We actually have many more techniques that we use to estimate distances, but these are the main ones. And notice that these overlap each other in some cases, so that way you can do a calibration. So let's start with radar and move outwards. Radar is a form of light, so here's Earth in the solar system, and we might send a pulse of light at Venus. Some of the light will bounce back, so all we do is see how long it takes for the radar pulse to get there and get back. Since we know the speed of light, we can find the distance. So we can do that to the moon. The astronauts left retroreflective mirrors on the moon, so it's easy to do to the moon. We can do it to the planets. You can't radar range the sun. It's plasma. The signal will be drowned out by the brightness of the sun. But what we really need to know is the distance between the Earth and the sun. Okay. So once you have radar ranging, it's not too bad to do. You just need a little bit of geometry. So you can take the sun, Earth, and let's use Venus. And if Earth sees Venus perfectly as a half phase, you know that this angle in the solar system is 90 degrees. We can use radar ranging to find this length of the triangle. We find this angle between the sun in our sky and Venus in our sky, and then we use geometry and we get this, 1 AU. So now that we know how many miles are in an AU, we can take that information and use it to understand parallax. Parallax is again using geometry, and we really needed to know that 1 AU before we could use parallax. And so you would watch from Earth and see how much this one star would appear to move compared to the background stars. And how much it appears to move is called its parallax. And if it's closer to the sun, it'll show more parallax. If it's further away from the sun, it'll show less parallax. And you use that along with the 1 AU, and you get a distance to the star. Okay. So this method of finding distances is fairly accurate. Okay. But the further something is away from the sun and from Earth, the less parallax it's going to show. So at some point we won't be able to use this technique anymore. We'll have to use a different technique. Another reason why this technique won't work as you're looking at more distant stars is that stars get dimmer the further they are away. So maybe our next step shouldn't be looking at one star, but looking at a whole cluster of stars. So we talked about how you can use an HR diagram to find the age of a cluster. You look for the brightest star left on the main sequence. Now you can use the main sequence to determine the distance of a cluster. That is called main sequence fitting. It's got a little bit of error in it. So here's an HR diagram of a cluster of stars, but instead of using luminosity over here, the amount of power, we used brightness. How bright does it appear from Earth? And the idea is that the main sequence will appear brighter if the stars are closer, and the main sequence will appear dimmer if those stars are further away, because we're going to assume that the main sequence is the same luminosity no matter where these stars are in the galaxy. So you need to have already known the luminosity of the main sequence stars. We needed to use the inverse square law for light, along with distances based on parallax, and to find the luminosity in the first place. But once you know the luminosity, now you can use that information over and over again to find the distances to other clusters. Cepheid variable stars are trying to maintain a balance between two fusion sources, helium in the core, hydrogen in the shell, and the solar thermostat will overshoot and then try to fix itself, overshoot in the other direction and try to fix itself. So these stars pulsate. They pulsate in color, they pulsate in brightness, and they pulsate in size. Now, a really interesting thing is how long it takes the solar thermostat to try to correct it really depends on the star's mass. But the luminosity is also dependent on the star's mass. All right, so let's make that a little bit more formal, put it in a graph. A more luminous Cepheid, which also has more mass, will take longer to pulsate. So how we use this is we watch it pulsate, and maybe it took 10 days for this type 1 Cepheid to pulsate. Right? That means its luminosity is at this value, and then you take that luminosity, you put it into your inverse square law for light, and you get a distance. If you're trying to find the distances to faraway galaxies, you're not going to be able to pick out a single star. They're too small to resolve, they're too dim to actually notice. Or even a cluster of stars, they're too dim to notice decently across the observable universe. So pick something brighter. How about a white dwarf supernova? White dwarf supernova all start out in the same way. They are in a binary system. They accrete more mass, and they hit the exact same mass limit, 1.4 times the mass of our sun. So when they explode, we're going to presume that they all come out with the same luminosity. Not perfectly, but close enough to get a really good estimate on their distance. And remember that these events are incredibly luminous. You can see these events across the observable universe. So how do we use this to get a distance? Well, we'd have to measure its brightness. We have to know its luminosity. So we've had to already figure that out through other means. But now we say we know its luminosity. So we use the inverse square law for light to find the distance. A standard candle is a light source of a known luminosity. And if you know its luminosity, if you know the amount of power it's giving out, you can use that to judge its distance. It's just the idea that if it's further away, it looks dimmer. So for standard candles, you're able to just plug in the luminosity. You've already found that value through other means. And then you ask, how bright is that object from Earth? And you plug that in and you get a distance. So now let's start Hubble's law. Hubble's law is also going to be able to estimate distances with very accurate results, 3% error. Edwin Hubble was trying to find the distances to many different galaxies. And this was back in the 1920s. So Edwin Hubble was using Cepheid variable stars that he could see in distant galaxies to estimate their distances. There's one extra thing that Hubble did that his peers had not yet done. For each galaxy that he found a distance to, he also got a spectra and determined its speed. So Edwin Hubble discovered this very odd and unexpected trend that all distant galaxies are redshifted and they're moving away from us. So in words, you could say Hubble's law says that the more distant the galaxy, the faster it moves away from us. So here is a graph of Hubble's law. It graphs speed away from us and distance from us. So the further it is away from us, the faster it's moving away from us. And that's weird, completely unexpected by astronomers back in the 1920s. I mean, what, does the Milky Way have a serious case of galactic chickenpox? The slope of the line is called Hubble's constant, and a lot of work has gone into finding this value as accurately as possible, because if we can find this value very accurately, then all we need to do is get a spectra of a galaxy, find its redshift away from us, and then in a matter of minutes, find out what its distance is from Earth. It's amazing. All right. You do not want to use Hubble's law for galaxies that are very close to the Milky Way. If you use it for galaxies that are close to the Milky Way, our gravity will actually change the speed of the galaxy, and it will throw off this trend. So you really only want to use it for distant galaxies. So if every distant galaxy is moving away from us, does that mean we're at the center of it? Maybe. But every time we've thought we were somewhere special in the universe, we've been wrong. So let's try to learn a lesson. So we call that lesson the cosmological principle. And it's basically that humans cannot be in a special place or in a special time. So how can we explain what Hubble found without being the center of the universe? We basically say that the universe is expanding. And the Hubble constant tells us how fast the universe is expanding. So let's explain this. Here is some raisin bread. It's the analogy every astronomy professor in every astronomy book uses. Okay? When you put the raisin bread into the oven, it will bake and expand. The bread will expand between each raisin, pushing the raisins further away, but the raisins themselves do not really expand. Only they'll plump a little bit, but they don't really expand. Okay? So think of the raisins as the galaxies, the galaxy groups, galaxy clusters. Gravity holds them together. They will not really expand. Space in between the galaxies will expand like baking bread. You're making more of it. Right? And so as time goes on, the galaxies get further and further and further away. So here we are in the local raisin. And if we look out, we see all of the other raisins moving away from us because the baking bread is pushing them away. And there's more bread between the local raisin and raisin 3, so that raisin will get pushed away from us faster. The more distant the raisin, the faster it moves away. Right? And here's a beautiful thing about the expanding universe. It doesn't matter which raisin you call the local raisin. Every raisin will see every other raisin moving away from it. Every raisin will think that they're somewhere special. The problem with this analogy is a loaf of raisin bread has edges, and a loaf of raisin bread has a center. So you can ask, does the universe have a center? Does the universe have edges? We don't know if the universe has edges at all. We cannot see to the edge of the universe. There's an observable boundary that we cannot see beyond. So we don't know. The universe might have edges. The universe might go on forever. The universe might wrap around on itself, and you might go too far east and come out from the west. We don't know. I might be able to give you a better answer about, does the universe have a center? So here's us at the present, and the raisin bread has already baked. It is quite large. And we try to look in the past and see when galaxies were closer together. Right? That's us finding the Hubble constant, finding out how fast has the universe expanded. Right? We can see back in time to a few 100,000 years after the Big Bang, and the universe was much, much smaller and much denser and much hotter. And we have a picture of the universe at that time. I'll show it to you in a couple of chapters. So imagine that this raisin bread was compressed down smaller and smaller and smaller to practically one single point. Right? That one single point could be called the center of the universe. And if that one center point were to expand into the entire loaf of bread, then every single point in that loaf of bread used to be in the center. So if you wanted, you could say that every point in the loaf of bread is the center, or used to be the center. I prefer to say that no place is the center. Asking about the center of the universe is like trying to divide by zero. It just doesn't work. Right? So the Hubble constant describes how fast the universe expands. So let's try to use that idea to gauge the age of the universe. Right? So if time goes on, so here's my graph. Time moves towards the present, and the present is the part of the universe that we're most sure about. It's easiest to see, we can touch it. Right? So here's us at the present. Right? And these lines here going into the past, getting closer and closer together, is going to describe the raisin bread getting smaller and smaller and smaller until it was at one single point. Let's call it the Big Bang. And so in this universe, we actually make it pretty far into the past before you have the Big Bang. Right? So that means that this universe model expanded slower. It has a smaller Hubble constant. Whereas this universe model shrunk down much more quickly, and the Big Bang happened much more recently in the past. So one way you could say that is an older universe, this one here, expanded slower. And so part of the reason we really want to know Hubble's constant really well is so we can find the age of the universe. And our best estimate for the age of the universe is 13.82 billion years old. And let's close out this video by ending with the full version of the Hubble Ultra 3D Field video.
Astronomers in 1996 attempted to do something extraordinary. They pointed the Hubble Space Telescope into a part of the sky that seemed utterly empty, a patch devoid of any planets, stars, and galaxies. This area was close to the Big Dipper, a very familiar constellation, and the patch of sky was no bigger than a grain of sand held out at arm's length. This was a somewhat risky move by the scientists. After all, observing time on this telescope is in very high demand, and some questioned whether it would be wasted trying to look at nothing. There was a real risk that the images returned would be as black as the space at which it was being pointed. Nevertheless, they opened the telescope, and slowly, over the course of 10 full days, photons that had been traveling for over 13 billion years finally ended their journey on the detector of humanity's most powerful telescope. Their feeble signals collected almost one by one. When the telescope was finally closed and the images were processed, the light from over 3,000 galaxies had covered the detector, producing one of the most profound and humbling images in all of human history. Every single spot, smear, and dot was an entire galaxy, and each one containing hundreds of billions of stars. Later, in 2004, they did it again, this time pointing the telescope towards an area near the constellation Orion. They opened the shutter for over 11 days and 400 complete orbits around the Earth. Using detectors with increased sensitivity and filters that allowed more light through than ever before, over 10,000 galaxies appeared in what became known as the Ultra Deep Field, an image that represented the farthest we've ever seen into the universe. The photons from these galaxies left when the universe was only 500 million years old, and 13 billion years later, they end their long journey as a small blip on a telescope CCD. These galaxies, while standing absolutely still, are racing away from us, in some cases faster than the speed of light. The space-time between us and everything else grows larger by the minute, pushing the galaxies in this image to a distance of over 47 billion light years. And because of universal expansion, the farther something is away from us, the more its light is shifted toward the red and the faster it appears to be moving. Edwin Hubble himself discovered this by measuring the redshift of many galaxies, and it's a measure of not only speed, but distance as well. Recently, Hubble scientists put the icing on the cake. Using the measured redshifts of our image, contact, forever changed by it. We pointed the most powerful telescope ever built by human beings at absolutely nothing, for no other reason than because we were curious, and discovered that we occupy a very tiny place in the heavens.